Hey everybody, how's everybody doing? Sorry for the long break. I just was kind of backlogged on a lot of work and stuff and didn't have enough time, but I promise I will start uploading consistently and finishing our Power 25 series, which is the 25 most essential LeetCode problems you need on a time crunch, right? So each of these topics are unique and they'll give you a very good running start to kind of acing those technical interviews. So without further ado, let's go ahead and get started. So this problem is so important. I've personally got asked this in around 3 interviews I've had. This is called subarray sum equals k. So, okay, so let's go ahead and get started. So given an array of integer nums and an integer k, return the total number of continuous subarrays whose sum is equal to k. Okay, so what are they trying to say? So these examples are okay. So nums is equal to 1, 1, 1. So it's saying, given this array called nums and a target value which is equal to 2, can you tell me the number of subarrays? So contiguous subarrays are subarrays that are adjacent to each other, right? So at index 0 and index 1, that's a contiguous subarray. This whole thing is a contiguous subarray, but index 0 and index 2 is not contiguous, right? So there's 2, right? Because the reason there's 2 is this one and this one, and this one and this one. Right, so yeah, so that's kind of the example. We have to output how many they form. So I kind of took a better example. So let's say that we have this example here, right? So the k is going to equal to 7. And let's see how many contiguous subarrays we can get. So how many contiguous subarrays we equal to 7? Well, we know this one is equal to 7. That's 3 and 4. We also know that, I guess we can do this. So that's 1. We know that this 7 alone is going to be a contiguous subarray. That's going to be 2. We know 7 plus 2 is 9, minus 3 is 6, plus 1 is 7. So this one here is going to be another one, right? That's going to equal to 7. That's going to be 3. And the last one here, the 1, 4, 2, is going at the end is going to equal to 7. That's going to be 4. So you're thinking, okay, that's a little bit hard. How are we going to get there? How are we going to end up doing this, right? So for these kind of things, right, let's think of the brute force first. So the brute force is, let's generate all contiguous subarrays that we have, right? So we can kind of go 3. So we have a subarray 3, right? And then we have 3, 4. Then we have, 3, 7. So we're kind of going here, our pointer's here. We do a double for loop and we kind of we generate all possible contiguous subarrays. And actually, no, we don't need to go 3, 4, 3, 7 because that wouldn't be contiguous. But you kind of see the idea, right? We're just generating all subarrays here. We go like 3, 3, 4, 3, 4, 7. Then we do 4, 7, 4, 7, 2. And that would be very costly, right? That would be O of n squared time because every index that we do, we have to iterate to n at worst case of those indices, right? So then here, and then if our pointer's at the 4, we have to iterate through all of these, right? And then etc. So that's just not going to be, what we want. That's not what we want. We want to solve this in O of n time. And I will show you a way how we can do this actually in one pass, right? So similar to the two-sum problem, if you haven't done the two-sum problem, I would highly recommend doing that right now. We can actually acknowledge this thing, and we can use a thing called a prefix sum. So what is this whole prefix running sum thing? So what I'll propose to you is if we generate a subarray of running sums, right? So what am I saying by this? So if I have a running sum array, so this is the running sum all the way to this index is just a 3, right? And then this one is going to be a 7. And then we're adding these, so it's going to be 14. So we're kind of, we're mapping this 1 to 1. And we're kind of increasing the running sum. So this is going to be 16, right? This is going to be 13. It's going to be minus 3. That's going to be 14. That's going to be 18. And that's going to be 20. So you're like, okay, yeah, well, we have a running sum array. What is this? What is the relationship here? So let's take a step back. We're looking for a subarray. We can say a subarray from index I to j. We're looking for a subarray from index I to j. That is a very bad looking j. And we're basically looking for a subarray such that, so how are we going to find this sort of subarray from I to j? Well, let's like kind of simplify this. Let's think of this example here. Let's just look at a 3, a 4, and a 7, right? So, okay, we have a 3, 4, and a 7. So if I want to get the subarray from 4 to 7, right? And I have the running sums of all of these. So let's say I have 3, this turns to 7, and this turns to 14. Well, the subarray from 3, so I want the subarray from 4 to 7. So I want index 1 and 2. So that's basically just the entire subarray, this entire running sum, right? Like the entire running sum minus, whatever's beneath it, right? So like, let's say that we want 3, 4, and 7. Well, it's basically just all the numbers from 0 to j. So this entire thing minus the elements from 0 to I minus 1. So that's just basically going to equal subarray of 0 to j. right? And minus the subarray from 0 to I minus 1, right? So that's all it is, right? It's basically this subarray ij is equal to all the elements if we were to just do all of them, right? When we're doing this running sum minus however many is I minus 1, and then boom, you get ij, right? So that's great. We have this subarray, we have this relationship, so you're saying, why do we need this? Well, if we kind of see this here, right? And let's say in front of a k which is equal to 7, and we have this running sum array. Well, if we can find a distance between these two running sums such that the distance between two of them, like the difference, is equal to k. So let's say that we have this running sum again, we'll just write it again, 3, 7, 14. And we find a distance that's equal to k, which is 7, we know that there exists a subarray in these two running sum distances, right? So this is the first running sum, this is the second running sum. If the distance is equal to k, there exists a potential subarray that sums equal to k. And that relationship is so crucial. So whenever we find a distance that's equal to k, or if our running sum itself is equal to k, we would just increment a counter. So you're saying, okay, well, we have this relationship. So subarray of I of j, right, that's basically just equal to k. K is just equal to our running sum, our run, let's say run s, minus our all the elements before the running sums, right? So minus, I'd say, previous sums, right? So k is equal to this, right? So if we do a little bit of algebra, and I'll show you what we can do here, and we just rearrange this, so we have our prev sum is equal to our running sum minus k, we've identified that with this formula, what we can actually do is something very, very important. So what we can do is we can actually create, like how we did two sum, we would create a hash table of all of our current previously quoted running sums. What am I saying right now? So let's say I have a 3. I'm going to store a 3 in the hash table. This is our first running sum, right? And all I'm going to say is if there's a previous sum that is equal to our current running sum minus k in our hash table, then we know we need to increment the counter. So what is this basically saying? So I'm going to start at this index here, which is a 3. So this 3, right, there's no -4, because if there was a -4, like let's say hypothetically, right, there is a -4 right here, then we know that the distance between this -4 and 3 is a 7, which is our running sum is equal to k, right? But right now there's none. So we say, okay, hey, is 7, so our current running sum is 3, right, and our k is 7, so 3 minus 7 is -4. Is -4 in our hash table? It's not, so we're just going to map the 3. And the 3 will have a count of 1, and we need to initialize this to a 0, and I'll explain that later. And we're going to go, okay, so we have running sum of 7, right? This is going to be a 7 here. Okay, so is 7 minus 7 in our hash table, right? Because we're doing our previous sum. Our previous sum is equal to our running sum right now, which is 7 minus k, which is 7, which is 0. Well, we found a 0 in the hash table. That just signifies when our current running sum is like a sum that we need, right? When our literal running sum is equal to k. So, okay, well, we need to increment a count, right? We just need to take the count of this, and our count is gonna equal 1. And, okay, so you have a 7. It's gonna be 1. Now we're gonna go to the 14, right? So we're gonna go to the 14 now. So what's gonna happen here? So we're gonna say, okay, well, our running sum is 14 now. So 14 minus k is 7. Is there a 7 that exists? Yes, right? There is a 7 right here. And now we would increment the count to 2. Why do we need to increment the count to 2? Because if we have this array of 3, 7, and 14, there is a distance between the 7 and 14 that's equal to k, which is 7 at this point. And you're saying, okay, that's great. And lastly, we need to update our running sum. 14 is going to be 1. We're going to speed through this a little bit more. Okay, so our running sum is 16. 16 minus 7 is 9. Okay, well, do we have a 9 in our hash table? No. So we just need to map our current running sum of 16. Okay, that's great. We have a running sum of 13. Okay, so 13 minus 7 is 6, right? Do we have a 6 in our hash table? No, we're just going to increment a 13 because there's no distances in this hash table that is equal to our k. Okay, we're going to keep going. We'll just use this. So now we have another 14. So you're thinking, what do we need to do for this specific instance, right? So we've recorded a running sum, and we found that, okay, we have a 14 here. That's great. And what do we need to do here? So we have a running sum. So 14 minus k, which is 7. So, sorry, 14 minus k, yeah, which is going to be 7. Do we have a 7 here? Yes, we do. We have a 7. And what we need to do, we need to increment the count because we need to increment it by the value that is present within this previous sum. So 14 minus 7 is 7. Okay, and now we just need to increment our 14 to a 2. Why do we need it? So you're saying, like, why do we need to increment this 14 to a 2? I will show you this right after. So now we have a running sum. Let's say our pointer's at the 18. So now we're going to have a 18 here. What's 18 minus 7? 11. Do we have an 11 in the hash table? No, there's no distance that fulfills equal to k. Now we're going to go 20. What's 20 minus 7? It's 13. Do we have a 13 in the hash table? Yes, we do. Right? We have a 13 right here, so it's going to equal, our count's going to equal 4, and then we're going to map a running sum of 20. So why is that here? It's because it's filling this here. 13 and a 20, that's a distance of 7. And you're saying, okay, well, why is a 4 equal to, why is there 2 things in the 14 here? Well, the reason is, let's say that I have another thing. Let's say that I have a 21, right, at the last index. So I have a running sum of 21. What's 21 minus 7? That's going to be 14. And okay, so if I get to this 21 and I find the reason I need to take these two 14s is because this 14 and this 14 both have distances of 7. So we can't just do one instance, we have to do both of them, however many the value is in here. So then in this case, it would turn to 6. Then we would map a 21 at the very end and we would break. So that is the coding implementation. We're using a prefix sum to kind of compound our elements, and we're using a hash table to store all of these prefix sums. And all we have to say is if due to the algebraic relationship we did here, if the running sum minus our k, if that value recorded of running sum minus k is present in our hash table, we know that we've found a susceptible distance such that the distance between two of the running sums is equal to k, and that's going to be O of n. Time complexity and O of n space, right? Because we'd have to, at worst, store all of these running sums in the hash table. So anyway, that was the high level, and we will go ahead and go to the coding implementation. All right, cool. So the high level implementation was a little bit more kind of than our coding implementation. You can see that our coding implementation is actually going to be pretty straightforward. So anyway, we're going to start with a previous sums, and that's going to be equal to our hash table is 0 or 1, and you're saying, like, why is there a 0 and 1? Let me just have this concrete of why we would have to initialize this here. This is the case when our actual running sum, you see how we have running sums here, right? When our actual running sum is equal to k, right? When our actual running sum is equal to k, like we literally have a running sum that's equal to k, then we need to sort of we need to save this value, right? The reason is, let's say that we land on a 7, that's a running sum. So it's going to do 7 minus 7, which is equal to 0. That's not gonna, if we didn't have this mapping, that's not going to map anything. So we need to keep this there as a default to say, hey, when our running sum is literally equal to k, we need to subtract that and cover this case, right? So just some kind of guidance on that. So now we're going to have a running sum. Set that equal to 0, and then we're going to have a counter. We're going to set that equal to 0. And we're going to do exactly what we did in the algorithm. So we're going to, iterate through all the numbers. And okay, so when we iterate through the numbers, well, we don't need to actually store it in a running sum array, right? We can literally just make a variable, and we can just say running sum is equal to nums of I. And now we just do we basically just do the algorithms, sort of the formula. So, right, how we said previous sum defined is equal to the running sum minus k, right? We kind of denoted that because we wanted to find a subarray of I of j, which is equal to the subarray from 0 to j minus the subarray of 0 to I minus 1. You can see, you can look back at the high level for that. And then we just rearrange the terms, right, through algebra to basically say, since k is equal to running sum minus previous sum, well, previous sum is equal to running sum minus k. So that's how we came to that formula. And now we're just going to say, well, if this previous sum to find, okay, so if that's actually, right, in our previous sums, that means we found a match, right? We know that we found something, at least one thing, where the distance between these two running sums are equal to k. So the count is going to actually plus equal the value previous sums of previous sum to find, right? It's actually going to equal the value of that in the hash map, right? Like how we established at the 14, we would actually do more, right? And yeah, so now, and at the very end, right? So if not, we would just say previous sums regardless of our running sum. It's just going to equal to previous sums dot get, right? So we're basically getting our current running sum to 0 and enumerating it to 1. So this is basically just saying, okay, we need to map all the running sums to our previous sums hash table, our current ones. And at the very end, we're going to be returning our counts. And let's see if this works. And like that, you can see it's submitted. We have O of n time complexity, of O of n space complexity, talked about in the higher level. And yeah, that's the problem, guys. Very, very important problem. I've got this in like 3 interviews. And yeah, hope you guys enjoy. Thank you so much for watching, and I'll see you in the next video.